Okay, let's get started. So today we will start looking at what is known as finite state Markov chains. Maybe I'll start with a simple example. Okay, so in this case, all the random variables are discrete. Okay, so I'm not going to talk about continuous time Markov chains or all the random variables involved are discrete, and there is the notion of state. Even the state is finite. Okay, so let's look at this. Okay, so let's look at a random walk. So what is a random walk in one dimension? So this is your 0, 1, 2 and 3, minus 1, minus 2 and minus 3. Okay, so person starting from here, let's say he's going to take a step right or left with certain probability. Okay, and then again the moment he suppose he's going to toss a coin with certain the bias. If it is head, he's going to move right or to the left. Okay, so that's what he's going to do. So by the time he, supposing let's say he reaches, let's say this state, then he's going to move to, let's say, 2 with probability. Suppose again he's going to toss the same coin. He's going to move to the state or the position 2 if it is head. Otherwise he's going to move to state minus 3 or the position minus 3. Okay, likewise here. So if it is a head, he'll move to 2 minus 2. Otherwise he'll move to 3. Is that fine?
Yes, sir.
Okay, so
So
now
that means it stays.
huh?
That means that's the limit -3 and 3. It cannot cross
Yeah, it
that.
cannot cross. Okay, I'm just looking at a finite state Markov chain because there is this notion of state. State corresponds to positions. Finite means there are finitely many positions. I'll talk about what Markov chains are. Okay, so now I'll denote this state by -3, -2, etc. 2, 3. Okay, these things. These are states. It's finite. Okay, and there's random variable. For example, x0 denotes the position of the person at time 0. So this will be 0 with probability 1. Okay, for sure assume that there is a bar or something and he's doing a random walk. So he's going to start at 0 with probability 1.
Sir,
Yes,
so is it necessary to have a symmetric around zero, sir, like plus
not
3 and
necessary. No, no,
no
no,
necessary, no, sir? Yeah.
not necessary. Okay,
Okay.
okay, okay. So let's assume that x1, okay, is going to be plus 1 with probability, let's say I'll make this simple. So p01 minus 1 with probability p0 minus 1. Okay, x2 is again, so basically okay, so let me make it very simple only. So I'll just use p minus p. Okay, so this is true only when I'll make it general xn nth
So
step.
always
Plus,
it
sir,
will be
Yes.
negative.
Hmm?
that should be 1 minus p, right?
Huh?
Sir, that should be 1 minus p. Second one.
Ah, this is 1 minus p. Yes, you are right. Good. So only when xn not equal to minus 3 or 3. Okay. If xn is equal to 3, sorry, xn minus 1. Okay, the previous one. I don't. What am I doing? No, no, no. Wait. Okay, so I'm sorry. Okay, let me use a different random variable. Okay, y0. Hmm? Y0 is the position. Xn is some random variable. Okay, so I'll define yn minus 1, the previous state in which the person is in. If it is not minus 3 or 3, then xn is plus 1 minus 1. Okay, if yn minus 1 is equal to 3, okay, xn will be what? What will be xn? It will be
Only
minus 4 with probability p, or minus 1 with probability 1 minus p, right? If yn is minus 3, you can fill the gap. Okay, so this now what will happen? So what is yn actually? Yn is
Hello, sir.
yn minus 1
Sir,
plus xn. Yes,
Hello.
yes,
it
yes,
is a
yes.
-3, I think, no, sir, in place of -4 because it is a.
Hmm?
So it will be -3, I think, no, sir.
Which one?
Sir,
Oh, sorry.
only, I
exponential.
think it's,
If it is 3, it should go to, if I add minus 1 to it, you go to 2 with probability 1 minus p, or you will go to minus 3. So it should be minus 6. Is this fine?
Sir, you said it will stay at that.
Okay, whatever. So, okay, so I'll slightly change. So you go to 2 or minus 3. Okay, it doesn't change the whole thing much. Is this fine, Rishabh? You can either stay or you can define it to go to 0 or 1 or whatever. Okay,
Okay, well, I mean deterministic. That deterministic.
it's not deterministic, it's with certain probability that happens. With certain probability you
Look,
stay,
the
otherwise
state
move on.
that I'm going, that is fixed from before
Hmm?
the experiment. I mean, the state that I will be going after reaching the limit, that is deterministic. With probability, I mean, the states are defined. I mean,
No, the states are fixed, minus 3 to 3. In which state are you in after n step is random, right? You don't know. It depends on what will be the outcome of the coin, right? Do you agree?
Hello, sir.
Yes, Ayush.
Sir, here the xn you have written in this page only. Plus
Mhm.
1 when probability is 1. P and minus 1 where
Correct.
when 1 minus p. So, sir, plus 1 with respect to previous step.
No, no, no. It doesn't matter. If I'm going to take a coin with bias P, toss it. If it is head, it will be plus 1. It's tail, minus 1. That's all.
So, plus 1 is the location where it is on the number line.
No, 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 no. So xn is something else, okay? The position is this yn. That's why I changed the notation, right? Y0 is 0. You start at 0 with probability 1. Okay, that will be your position at time 0. At time 1, what will be the position? You can calculate from this, right? Yn, y1 is y0 plus x1. Y0 is 0, so it will be x1. So, for example, x1 is 1, then you go to 1 from 0. If it is minus 1, you go to minus 1. Okay, what will happen subsequently? You will add or subtract to the current position with certain probability. If you are in 3 or minus 3, then the one that you subtract or add will be different. It will be minus 6 and minus 1. Is that fine?
So, how did we get this minus 6 and minus 1? Can you explain once again?
For example, if you are in 3, right? Okay. With probability, let's say it goes to 2 with probability p, or it goes to minus 3 with probability 1 minus p. That's the definition. That's how I have constructed my chain. Okay. If you're not happy with that, you can say, well, you go to 2 or 1 or 2, or you stay back, whatever you can define.
Okay, so the xn is defined by us here. So it is not
Yes, yes.
being calculated.
No, no, no. So everything is defined. Nothing is calculated now. So I'm going to define. If you're not happy, you can just say with probability P, if you are in state 3, with probability P, you go to state 2, or you stay with probability 1 minus 3, you stay in state 3. That is also a valid Markov chain. Okay, whatever Markov chain means. Okay. Now, what you can see here is this xn's are IID. Okay. So these are all not IID, independent. Because the way I'm going to toss the coin, they're all independent. Okay. So now with this, what can you say about xn? This is a stochastic process, right? N equal to, so not xn, yn, n equal to 0, 1, 2, etc. This is a stochastic process. It's a discrete stochastic process because n is discrete, as well as yn also takes finite values, right? Is this fine? So what is it that you can say about this yn? See, yn given yn minus 1. So the future state in which you will be in, the immediate future state that you will be in, is independent of all the past given the current, right? For example, if you are here, right, the future state. So suppose I come here, right? The probability or the chances that I come here, given the previous states, it depends only on the immediate previous, right? Because I cannot come. You understand what I'm saying? Hmm? So what I'm saying is probability of yn equal to some state in, given yn minus 1 I was in some state in minus 1, yn minus 2 I was in some state in minus 2, etc. y1 I was in state I1, because y0 is anyway 0 with probability 1, so I need not even condition on that. This chance, right, depends only on the immediate neighbor.
Hello, sir.
Yes.
Sir, is it also true for the extreme case, like when after yn equal to 3, I go to minus 6? This can also happen if I am in minus 2 position and I get a tail. I go to minus.
Yes. It's possible. So what I am saying is the chances depend only on the previous state. It doesn't depend on all the previous. Okay.
Okay.
So it doesn't matter which path you took to come there. It depends only on what is it that you were in the previous state, previous time slot. That's all. Is this clear?
Yes, sir.
Intuitively clear. I mean, we can rigorously show this, but is this clear?
Yes, sir.
Yeah. Okay. Actually, this follows from definition, right? So what is yn? I can write this, right? Yn is yn minus 1 plus xn, right? So yn minus 1 is conditioned on in minus 1. So it becomes xn is equal to in minus 1, right? So xn is independent of all yn minus 2, yn minus 3 by construction or by definition. So it depends only on. So okay, let me write this. Okay, this is how you generally prove. What is yn? Yn minus 1 plus xn is in, given all this, right? So this is equal to, so there is a yn minus 1 equal to in minus 1, right? So since I'm conditioning on this, this will be in minus 1 given all these, right? So now by definition, this is nothing but xn equal to in minus 1, because it doesn't depend on anything else, right? Because xn is independent of everything. But this I can write it as probability of xn equal to in minus 1 given yn minus 1 equal to in minus 1. Because xn is independent of yn minus 1, conditioning doesn't change, right? So both are equal. So what can I say about this? I can say in minus 1 is yn minus 1. So I can say yn minus 1 plus xn is equal to in given in minus 1 equal to in minus 1, right? This is nothing but probability of yn equal to in given yn minus 1 equal to in minus 1, right? This is the computation. So essentially what I have shown is conditioning on everything depends only on the immediate past. I have actually proved it. Now, is this clear? Okay. Shall we define what a discrete time Markov chain is? Is this fine?
Yes, sir.
Yes, sir. Yeah.
We say that xn etc. xn belonging to some state. The state is the number of elements in the state is finite. Okay, is a Markov chain if probability, note that I'm using xn here because in the previous case yn was the Markov chain, but anyway, xn equal to in given xn minus 1 equal to in minus 1, etc. x0 equal to I0. This is equal to probability of xn equal to in, okay, given xn minus 1 equal to in minus 1. For every in minus 1, you take any state, okay, we say that it's a Markov chain. Is this fine, this definition? This is conditioning. Probability of A given B is probability of AB divided by probability of B. Okay. Okay. Is this fine? Any questions?
No, sir. Means, sir, it only depends on the immediate previous situation. No, sir. That's we are trying to say over here.
Sorry, what is that?
Like, sir, in this definition, sir, we are just saying that this process will be Markov chain if it only depends on the immediate previous
Immediate previous,
situation.
and given the immediate previous, it is independent of all the past.
Yeah. Yes,
Okay.
sir.
Hello, sir.
Fine. Yes.
Yes, sir.
Sir, it's like memoryless, right?
Yes, it is a memoryless property. Yeah, it kind of forgets what happened
I mean,
before
every
given the
time
immediate
it
past.
comes to a position, it starts up
Huh?
fresh.
Yeah. So given that you are in some state, the future is independent of what happened in the past. It only depends on where I am now. Okay. What happens tomorrow depends on what I am today. Doesn't matter what I did in the past. Then it's a Markov chain. It's memoryless property. Yes. Okay. Is this fine, everyone? Okay. If you say
Yes,
yes,
sir.
I'll proceed. Huh? Huh?
Yes, sir.
Yes.
Yes, sir.
Okay. Fine. Okay. So now there is a shorthand. There's some notation. This transition, right? Probability of, for example, xn equal to in. So I'll make this little easy. So let me not write it like this. I given xn minus 1 equal to j, I'll use a shorthand for this. Okay. So this is from, okay, I'll just exchange this. Okay. I'll call this as j and I'll call this as I. I'll write this as p ij of n. Okay. Why pij of n? Because, for example, when you looked at this Markov chain, right? This particular Markov chain, you used a coin. The bias of the coin was fixed at p. Okay. But what if I use different coin as in time progresses? That means I'll have different biases. Then the transition probabilities, these are called transition probability. Okay. This is called transition probability. Okay. This transition probability will change over time. It's possible to construct such a Markov chain, or it's possible that there are Markov chains with this kind of change in the probabilities. Is this fine?
Hello, sir.
Yes.
That this probability is same as probability of yn equal to +1, right?
Which yn? The example?
No, no. In this yn is this
There is no
tossing.
yn here, right?
No,
There is xn.
I'm defining it as tossing of it, random variable,
Huh?
tossing of coin, related to tossing of coin.
Tossing of a coin is an IID process, right? It's a trivial Markov chain. Nobody wants to. I mean,
No, sir. This is same as getting head on when we are standing at the x minus ith position.
no, it depends on what j and I is, right? So it's not just head.
Okay, fine.
It can go to multiple. You can probably throw a dice also, right? Depending on the outcome of the dice, you have two dice. Let's say one is marked 1, 2, 3, 4, 5, 6. The other one is marked as -1, -2, -3, -4, -5, -6. You pick one of them randomly and throw whatever outcomes you get. Whatever outcome you get, you will just move by that distance. If it is a +2, you'll move +2. If it is -5, you move back to the left by -5. Something like that. Okay.
Yes, sir.
Okay. If Pij is of n is independent of n, and then we say that the chain is a homogeneous Markov chain. Okay. So that means I'm going to use the same dice or the same coin over time. I'm not going to change it. So the transition probabilities remain the same, irrespective of what n is. Then we say that it's a homogeneous Markov chain. Is that fine? Okay. Okay. So now let's look at a few other things. So I'm going to construct a matrix out of it. So let me call this as P.
Hello, sir.
P. Yes.
Sir, here n is the time instance, right?
You can think of it as time or whatever you want to. So not just time, right? So you can be looking at examples where n need not necessarily represent time. It can represent some index or something like that, right? So for concreteness, you can assume n to be time slot.
Sir,
Yes.
so you just mentioned in the definition that it is a Markov chain if it depends upon the previous immediate previous position. No, sir.
It
But
only depends
in
on yes.
yeah, but here you are saying that it is independent of n. So how could it be independent of n? Because it always depends just previous situation. No, so like
Previously
if
depends, but it doesn't depend on at what time you are looking at, right? What is this probability? This probability in minus 1, right?
yes,
So
sir,
for
yeah,
example, in is 2, in minus 1 is
3. So that's
1,
one,
right?
one,
Huh.
yeah,
So what is in minus 1? 1. So probability of
yeah.
xn equal to 1 is what? P,
P,
right? So this
yes,
probability
sir,
will be P, right? So on the other
yeah.
hand, so it doesn't matter, right? So if in plus 1 equal to 2 and in equal to 1, and you are looking at probability of xn plus 1 equal to in plus 1 minus in, still it's P, right? Doesn't matter at what
Oh,
time you are looking at the transition, right?
okay, sir. Okay.
Okay. I'm using the same coin all the time. That's what it says. So how
Okay.
many rows should be there here? Any idea? Okay. Just to be consistent, I'll just see what the book uses. He uses M. Okay. So I'll assume that there are M states. So basically, the cardinality of S is M. Okay, that's what I'm assuming. So this will be P21, P22, etc. P2M, and
Hello,
so
sir.
on. PM, yes.
So some of these elements of these rows should be zero, right? I mean, it cannot go to every state from one state.
It can go to any state from one state, right? We will see that. Okay.
Okay, okay.
We will study that in detail now. So this is a matrix which describes the transition, right, from one state to another state. For example, if you are looking at a transition from ith state to jth state, it's Pji,
Hello, sir.
right? Yes.
The sum of the rows should be equal to 1, right? Sum of the rows are the columns.
Can you tell me which one is true? Okay, I haven't. So what is P12? You are starting a state 2 and you are going to state 1. That's what it says.
Probability of going from any state to state 1 is 1.
Hmm?
Total probability.
No, probability that you start at a state, let's say I, going to some state out of that or in any state, right? It could even remain, should be 1, right? If something should happen if you are in state I, you should either remain in state I or you should go out of state I, right? The probability of something to happen given that you are in state I is 1. That is nothing but what?
Columns.
Columns are one.
Clearly. So if you look at, for example, Pij, you are in state J and you are going to state I. So summed over all I should be 1. Okay. This is clear?
Sir, can you use the notation PJI? I mean,
Hmm?
sir, I mean, can
Did
you
I
use the?
use?
Yes, sir. Use JI.
Okay. So no. It's, see, this is Ij. That means,
Okay.
the 1 second. Let me just verify this just to be consistent with the book. So Ij is from I to J. Okay. Ij is from I to J. This is correct. You start at I and go to J. This is Pij. Okay. You start at I and go to J. This is Pij. So you're starting at I. Okay. So this is correct. So Pij, right? from all j. So you start at I and you go to some state j, is the sum is 1. Is that clear? Why is that? It's basically, if you are going to state 2, you look at two events. You are going from I to state 1 and I to state 2. If you look at these two events, these two are disjoint, right? Because if you go to state 1, you cannot go to state 2. So these are disjoint events. But if you look at going from state I to some state j and you exhaust all possible state j, that will give me the entire set omega, right? The sample space. So probability of union of these events, given that you are in state I, should be 1. But since this is disjoint, you can write it as sum. Okay, I'll leave this as a homework for you to get, convince yourself that this is true. Everyone, this is fine, right?
Yes, sir. Sir, one more thing.
Yes.
Is this matrix P
Hmm.
a symmetric matrix?
Okay, can you think of whether it's symmetric or not?
Sir, I'm saying this because, sir, the probability from going from I to J, like from 1 to 2, and will be same, might be same
Not,
for 2
It's
to
not,
not symmetrical.
not necessarily, right?
P1 minus P2.
Hmm? No, not necessarily, right? Okay, before that, this matrix P is called probability transition matrix. Okay, or transition probability transition matrix, right? I think this should be probability transition matrix. Okay. So now coming back to your question, so I'll take a very simple Markov chain. So from now onwards, I'm going to write it in this fashion. Okay. So there are only two states, 0 to 1. Let's say there is a frog in the pond. It can either jump out of the pond or stay inside the pond. It's going to jump outside the pond with probability P1. Okay. With probability 1 minus P1, it will stay inside the pond. If it is outside the pond, it can go to jump into the back into the pond with probability P2, or it can stay back with probability 1 minus P2. This is a pictorial representation of the entire matrix. So how do you write this? Let's say 0 1 0 1. Okay, if you go by this, right, P1 P1 2, right, this is P0 0. What is the probability? 1 minus P1. This is P11. This is 1 minus P2. So what happens to this? 0 1. That means you are in state 0 and you are going to state 1, which is P1. This is P2. Okay, fine.
So that means we can design it to be a symmetric, but it not necessarily be a
Not
symmetric.
necessarily symmetric.
Yeah.
Yes, most of the times it need not be symmetric. Fine. Okay, any questions? And needless to say, Pij is greater than or equal to 0 for all ij. Okay, this is also true, right? These are some of the properties that we can immediately infer from the probability transition matrix, right? Okay, any questions so far? No?
Sir, PIJs are the probabilities, no, sir?
Yes, Pij.
So it should be 0 to 1 only, I think.
That is also given,
Yeah,
right? So
yes, sir.
these two put together will ensure that it's between 0 1,
Mhm.
right? Okay, so now let me ask you one other question. So probability, okay, that you are in, let's say n plus 2, let me just write it like this. Okay, so after n step you are in state j. Okay, I'll just let's go back. Ij is ij. Okay, I to j. Okay, fine. So you are in state, let's say n minus 2 is I. How do you compute this? You understood what this says, right? N minus 2, that is 2 steps back you are in I. Now, what is the probability that you will be in state J after 2 steps? How do you write this? What is this? Can you compute this? Can you try?
Yes, sir. You can write xn is equal to z conditional xn minus 1 and product xn minus 1 is conditional xn minus 2.
Okay, good. That's enough. That's enough. Huh? Okay, so let's take a very systematic approach. So what is this? I can xn equal to j is an event. I can intersect with the entire omega, right? Nothing will change. Do you agree?
Yes, sir, yeah.
So I'll intersect with xn equal to j. Okay, xn minus 1 equal to k, given xn minus 2 equal to I. But xn minus 1 equal to k is just one event. It's not the entire omega. If you sum it, essentially I have to take the union over all k. Okay, then I'll get the entire omega. Since these are all disjoint event, union becomes the sum. Is this fine? This is clear? Fine?
Sir, I just one doubt. Sir, in this general case, I mean general Markov chain, I mean from in every state there is a probability of going to every other state.
Not
And
necessarily, not necessarily.
then sir, some of the case should be redundant, right?
Meaning?
Sir, there is probability of xn equal to j, comma xn minus 1 equal to k. So there may be some states from that we cannot go to the jth position or jth state.
Then that will be 0, that's all. So I can always write this, right? There is nothing wrong in writing this. The probabilities could be 0. Then I'll be counting 0 for towards that. That's all.
Okay.
Okay. So now I can write this. This is clear, right, everyone? This I can write probability of AB given C is probability of A given BC into probability of B given C, right? Given xn minus 1 equal to k, xn minus 2 equal to I times probability of xn minus 1 equal to k given xn minus 2 equal to I. Okay. Now let's look at this summation over all k. What can I say about this? Xn equal to j given xn minus 1 equal to k and xn minus 2 equal to I. Well, it's independent of the past, right? It only depends on
xn minus 1.
1 equal to k. And this is what P, well, now it's a homogeneous Markov chain. This transition from I to k does not depend on n, right? The time step. So it should from I to k. Okay. What is this? This is summation over all k. The first term is, I don't know, there's some issue with the got stuck.
Okay.
Hey, just sorry, man. So I'll just hope okay, good. Oh my god. I'll quickly, can I directly write this? Is that okay?
Yes, sir, yeah.
So this is what? Summation over all k. The first one will be, I go from k to j, and then the second one will be I to k. Is that fine? Let me just check I get confused with the notation. So I to j is I to j, okay. I to j is ij. So k to j, that's correct. So k to j and I to k and k to j. Okay. Is this fine? Okay. So
Yes, sir, yeah.
what is this? So this is the probability that you start at I and go to j in 2 steps. Okay. I'll write this as follows. Okay. I start at I, go to j in 2 step. Okay. This is the notation. So essentially I start at I, go to j in 2 step is summation over all k. I start at j, go to k, and then from k I go to I. Sorry, the other way, right? I start at I, go to k, intermediate state. From k I go to j. I take all the intermediate. So pictorially it's like this, right? So I start at I, go to some state k, right? Some whatever state it may be. It could even be I itself, okay? And then I go to state J. Okay. So if you sum over all possible intermediate state, that gives you this. Can somebody tell me, based on your linear algebra, simple algebra, right? In what does this corresponds to in terms of matrix?
It's inner product of ith row on jth column.
Correct. So what does that corresponds to?
It's,
Covariance.
Oh my God, what is covariance, man? These are probabilities, right? You take p squared, you take the matrix P, take p squared,
multiply with itself.
and look at the ijth element of it, right? You take p square matrix, look at the ijth entry of it, that will be pij2. Fine. Okay. Now let's look at what might happen if I were to write or if I were to get Pijn. What do you think is the answer? Any idea?
Should be p
There
power.
will be n steps like summation over k.
P power n ij.
Yeah,
Right?
in terms of matrix,
This is
yes, sir.
guess. Okay. This is something that we can guess easily, right?
Yes, yes, sir.
But now, how do you prove this? Any idea?
Similarly said as above we have done.
No, you come from math background, right? So what is it that you will do if you want to prove this kind of a general statement?
Induction.
Induction, sir. That's
Right?
right.
So you have to do induction. So I'll leave this as an exercise. Okay, use induction to prove this. Okay, so this result is called Kolmogorov-Chapman equation. So I'll not. What happened? Okay, this result is called Kolmogorov-Chapman equation. Okay, I won't write this formal result. I'll leave it as an exercise. It's easy, straightforward. Okay, so now you know, right? If you start at state I and if you want to go to state J in n steps, that is n time slots, that probability is nothing but you take the probability transition matrix, raise it to the power n, look at the ijth entry, that will give you the probability. Is that fine?
Yes, sir.
Okay. Now, let's look at a few other things. Okay, so now from this we know that I can write these states as circles, right? We saw that here, right? We can write these states as circles and transition probability as some basically the entire Markov chain can be encoded as a graph, right? With the node being states and edges being, in fact, it's a directed edge being, it's a directed graph, and the weights being the probability. Is that okay? Is that fine, everyone?
Yes, sir.
Okay. Now with this, we'll look at a few definitions. Okay. Let's look at a few definitions with this encoding. Okay. Okay. So first thing is n-step walk. How many of you are familiar with the graph theory, elementary graph theory? Yes, sir. No, you just have to answer. No.
No, sir.
Okay, fine. No problem. So what is an instance? So I'm considering Markov chain encoded as a graph, okay, directed graph. You can imagine what the picture, right? So what is a walk? Basically, you go from one state to the other, right? That is a walk, right? In fact, it's an ordered walk. Ordered string of nodes. Okay. So for example, I0, I1, and so on, In, n greater than or equal to 1. That means I start at state I0, immediately I go to state I1, and so on. After n steps, I go to state n. Okay. Such that Well, there should be an arc from I0 to I1 and I1 to I2 minus 1. What does that mean? That means that the probability of you going from I0 to I1 in one step should be non-zero. Probability that you going from I1 to I2 should be non-zero, and so on, right? That's what it means, right? Probability of you going from Im minus 1 to Im is non-zero. If this probability is zero, there is no arc between the two states, right? The arc would be vacuous because the weight will be zero. Okay. So what does this mean? So for example, if you have let's say I take this thing. Okay, this is a state 3. This is a typical walk, right? I go from 0 to 1, 1 to 2, 2 to 3, and so on. And this, okay, now I'll write the typical walk. So you go from 0 to 1, 1 to 2, 2 to 3, 3 to 1. Okay, this is a walk. Note that I've started at 0, went to 3 and came back to 1. So I have entered the state 1 twice. Okay, but still it's a walk. Okay, is that fine?
Yes, sir.
Okay. Now the second thing is what is known as a path. Okay.
Sorry, sir, I missed the point.
See, you start at 0, went to 1, 2, 3, and back to 1. That's a path, right? And you could have, for example, if there is a path like this, I mean, if there is a link, then I can even go back to 0 also. That's also a path. Or I can go from 0 to 1 to 2. That's also a path. So essentially, all possible traversing. Okay, you
that
take
means
any traverse. That's a path.
in a
That's
path
a
I
walk.
can cross a node more than one times.
Yes, yes, that's a walk.
Okay.
Okay, there is something known as a path. Okay, so path is a walk with no cycles. Okay, walk without entering the same node again. Okay, without entering a node twice or more, or it's a walk. I'll just simplify this. Okay, basically it's a walk in which no nodes are repeated. Okay, this is the path. Okay, so clear, right? You cannot circle, you cannot come back to some state. Okay, there is something known as a cycle. What is a cycle? Again, it's a walk in which the last and first node are the same, and in between no nodes are repeated. Okay, walk with first and last nodes being same while no nodes repeated in between. Okay, is this fine? Cycle is like
Yes,
this,
sir.
no repetitions. Okay, there are nodes in between like this. Okay, path is no repetition. It's a walk, but there is no repetition of any node. At least you start here and come back here. At least this node is repeated in cycle. Only this node is repeated. Okay, that's a cycle. Walk is arbitrary. Okay, path is without cycle. Okay, fine. Okay, now with this we'll look at a few definitions. So now I have encoded everything into a graph, right? The entire Markov chain. Okay, we say that a state J is accessible, okay, from I, denoted So basically, state I can go to state j. Okay, that's what it means. State I can go to state j. This is with the notation. Okay, if there is a path, right, or a walk, there is a walk from I to j. What does this mean? Any idea? If there is a walk from I to j, what does that mean? I can start at I, that means the probability that I start at I, go to j, in some step, let's say L is greater than 0 for some L. Okay. Then we say that state j is accessible from state I. Is that fine?
Yes, sir.
Okay. Now, okay, I'll write one more thing and distinguish the two. Okay. Suppose you have two states. Okay. There's some, I don't know. I think maybe I have to change. Oh, what happened? Oh my God. Okay, so I'll sorry about this. So I'll continue with whatever I was discussing. So okay, so now we say that I communicates with J if, of course, denoted I J, if I communicates with, I can talk to J and J can talk to I. Okay, is this fine? Okay, is this fine, everyone?
Yes, sir.
Clear? Huh? Okay, yeah. So now let's see what is this. So if you have a state, right, with, let's say, some states, and you have a Markov chain with certain states, finite states, with this notation, right, communication, let's say I and J communicates, this notation, this will split the entire chain into a group of states. Let's see what does that mean. Okay, let's see, first of all, okay, so let's look at properties of this. Okay,
Hello, sir.
Yes.
Sir, I and J are accessible. I mean, the first notation, I right arrow to J. Sir, doesn't that imply J can also come to I?
No, not necessarily, right? Not necessarily. See, in the first example itself, from 3 you can go to -3, but from -3 you cannot go to, you can, okay, in that case, but I can give you an example. Okay, so we will see. Maybe I'll give an example and then start the property. Is that fine? Okay, I'll just give an example. 0, 1. Okay, so it goes here with probability P, here with probability P. Okay, it comes here, or stays back with probability 1 minus P, 2 with probability 1. Now what will happen? See, from 1 it can either, sorry, what is this? No, sorry, this is what, if it goes out with probability P, it can go over here with probability 1 minus P and 1. What can you say about this? See, from 1 to 2 there is a non-zero probability. If I am in state 1, there is some non-zero probability that I can go to state 2. But there is no return from state 2, right? The moment I reach state 2, I cannot come to 1. So 1 to 2 there is a communication, but there is a path, but from 2 to 1 there is no path, right? Is this fine?
Yes, sir.
Huh?
Yes.
Well, 2 is called absorbing state. So because the moment you go to 2, you'll stay there forever. Okay.
Okay.
Okay. So I communicates with I. Why? Clear, right? So because Pii in 0 is 1, which is greater than 0, right? That's the definition, right? So I communicates with J. That means Pij, right? I communicates with J means what? You start at I and you go to J, right? Pij. So Pij of n is greater than 0. That means in n step for some or L, in L step, you can go from I to J with non-zero probability, right? But I communicates with I because Pii of 0 is 1 because you're already there. Fine. Okay. I communicates with J implies J communicates with I. Trivial, right? Why is this trivial? By definition, right? Pij,
Yes.
yeah, so it commutes. See, if I communicates with J and J communicates with K, implies I communicates with K. How do you prove this? So what does this mean? This means that there is a path from I to J. That means with non-zero probability after some steps K. So let me write this. This is the proof, right? So Pi to J in L step is non-zero. Pj to I in some M step is non-zero. Okay, that's what this means. What does this mean? This means Pj to K in N step is non-zero, and K to J in just give me K step is non-zero. Okay, is that fine? So if what is it that I have to prove here? First thing that I have to prove is Pik in some step is non-zero, right? So I have to say this is non-zero. I mean, it's greater than 0. So what do you mean by that? So I can write, so clearly I can go from I to J in L step and J to K in N step. So I to K in L plus N step, right? At least. Do you agree?
Yes, sir.
Okay. So that means I can go from I to K in L plus N step. What is this? This is, I can write this as what? Summation Pi to J in L step, P J to K in N step. Okay. What should I sum over? I should sum over all J, right? All possible J in between, right? Well, just to avoid the confusion in notation, this J can be, give me some other variable. No, let me call it as O. Okay, O is some state, in between state. Okay, O. But definitely I'm summing over all state O, but one of them is J, right? Do you agree? There will be something like OJ in L step, JK in N step. Do you agree? This will be one of the terms in this summation. Do you agree?
Yes, sir.
So this will be greater than this. Do you agree?
Yes, sir.
So that will be greater than 0. Because why? Because of this and this. This will be greater. So that means Pik in L plus N step is greater than 0. So you interchange the role of I and K, you will get Pki in some steps will be 0, greater than 0, right? Same proof. Do you agree?
Yes, sir.
Is that
Sir,
fine?
hello, sir.
Yes.
Sir, is it possible that I go from I to J in L step and J to K in N step? But maybe when I go from I to K, there will be some O, I mean some intermediate path that
Exactly. Yeah, you can probably go in one step also. You never know.
yeah.
Yeah. But what I'm saying is there is some number of steps using which you can take so many number of steps, some finite number of steps, and reach that state. That's all I'm trying to say. Okay, I'm not saying lesser number of steps is impossible. No, you can in fact go to the other state in one step only. We don't know. Is that fine?
Yes, sir. Yes.
Okay. So Sumit, can you tell me what can you infer from this? I communicates with I communicates with J, and J communicates with I communicates with J, and J communicates with K implies I communicates with K. What is this called?
It's a relation, no, sir.
What
Equivalence relation.
exactly, right?
Yes, sir.
So okay, those who don't know this communication, whatever this notation brings in an equivalence relation among the states. Okay, why is it called equivalence? So for example, A is equal to A, right? If A equal to B, then B equal to A, right? If A equal to B and B equal to C implies A equal to C. So it satisfies or mimics this equality, but it's not really equal to. So it's called an equivalence relation. This is called equal to relation. This is in general called equivalence relation. Okay. So what is the impact of what is so the moment I say there is an equivalence relation, so this implies
Dual
this,
partition.
yes, this is an equivalence relation on S, the set of states. So what does that imply?
It will
This,
partition the S.
yes, right? Partitions, yes, right? Into what?
Equivalence classes.
Yeah, equivalence classes. Within those classes, the nodes can communicate with each other. Outside the classes, it cannot. So let me give you an example. So 0, 1, it can communicate. Okay, so it goes back and forth. And there is 2, 3, it can go back and forth. Okay, now there can be communication across. Okay, so maybe there is, okay, so with probability, let me write this. So this goes with probability P, 1 minus P. This comes here with probability P, or goes here with probability 1 minus P. This is P and 1 minus P. So yeah, this is again P. What kind of a Markov chain is this? See, the moment you go to this state, right? For example, this chain here, the entire is one Markov chain. But the moment you enter into one of these states, that's it, right? You cannot come back. You will be stuck in 2, 3. But you'll go back and forth from 2 to 3. So 2 communicates with 3. So this forms an equivalence relation class. 0 communicates with 1. So this forms an equivalent class. But the moment you go out, you are done, right? It partitions into 2 classes. Is that fine? Do you agree?
So that
Because
means
Yes, sir.
0 doesn't communicate with 2, right? Because the moment you go from 0 to 2, yes, there is a probability 1 minus P, but you cannot come from 2 to 0. So 0 and 2 does not communicate with each other. Yes?
so that means there will be equivalence relation within classes in S.
Yes, so I can say whether, if you give me 2 classes, I can say whether it communicates with each other or not. That will sort of, I can group them, right? All the states which communicate with each other, I can group it into one basket, right? Oftentimes what happens is all the states will be in that one basket. There'll be no other states left over. But in this case, what happens is in one basket I have 0, 1 because 0, 1 communicates with each other. There is another basket 2, 2, 3 which communicates with each other. So there are 2 baskets, right? So equivalence relation is sort of partitioning it into 2 baskets.
Hello, sir.
Yes.
So was it necessary for a connection from 0 to 2 to be called equivalent?
Yeah, I mean, if you remove this, right, connection, then it's too trivial, right? You are taking 2 different Markov chains. Why do you want to consider it as one? Of course, you can do that if you are okay. So this is very trivial, right? This is a, now what can you say? So 0, 1, this is one Markov chain, this is another Markov chain, right? Of course, you can combine them and say, well, transition from 0 to 2 is happens with probability 0. That's as good as taking 2 different Markov chains, right? Do you agree?
Yes, sir. Sir, I mean,
Yeah.
sir, the notion of equivalence
Exactly.
comes.
So You are right. If I consider 0, 1, 2, 3 as one, if you consider these two as one Markov chain, equivalence relation will split it into two. 0, 1 will fall in one basket, 2, 3 will fall in another basket. In this case, those two are different Markov chains altogether. You can treat it as different Markov chains. But the moment I put this, right, 1 minus b, I cannot say that these two are different Markov chains. They belongs to the same Markov chain, but different. I can split this into two different equivalence classes. Okay,
Okay.
is that fine?
Yes,
Yeah.
sir.
Okay, so we will continue with this in the next. Okay, so I think the big picture wise, what is it that we are trying to do? Maybe I'll describe this in the next class. Okay, so I probably should have done this before doing this equivalence. Okay, just read what is equivalence relation and try to see why it partitions the set into disjoint subsets. Okay, just read through that, but otherwise this is what it is. Generally, the big question that we are asking is whether there is a stationary, what is known as stationary distribution for a Markov chain. That is the big question that we are asking. Okay, it has its own advantages. We'll see what are those advantages. Is that fine? Okay.
Yeah, okay, sir.
Okay. So I'll stop here. In the next class, we will continue with this Markov chain further. And then this time, I thought I'll also teach a little bit of Markov decision process (MDP). Okay, which is a part of this, and luckily that's there in the book as well. I mean, it's a part of this chapter, so I'll do that as well, so that you know what MDP is. Okay.
Okay, sir.
Okay. Yeah. Is that fine, Ayush?
Yes, sir.
Okay. Praveen? So
Yes, sir.
remember, we'll have a quiz next week. So start preparing. Okay.
Okay, sir. Okay.
Okay. So
Okay, thank you, sir.
yeah. Thanks and happy Deepavali. So
Thank you too, sir.
we'll,
Happy Diwali, sir.
yeah. Thank you. We will meet